Welcome back, my dear students. Last class we have started discussing about the method for handling deadlock, and we have seen three ways for handling deadlock. In this class we will be discussing about deadlock prevention. We already discussed about the four necessary conditions to have deadlock. We discussed it in our offline class. The necessary conditions are mutual exclusion, hold and wait, no preemption, and circular wait. Hope you remember that one. If all the conditions are true, then there is a deadlock prevention says try to remove at least one of the necessary condition. If any one of the condition get false, the deadlock will be prevented. This is the idea behind deadlock prevention. The first condition is mutual exclusion. Let us just recall what was mutual exclusion. Whatever the resource you are sharing, they should be non-shareable. Means they should not be used simultaneously by multiple processes. If multiple processes can use the resource simultaneously, then we can say there is no mutual exclusion. If you want to discard mutual exclusion, then we have to make all the resources shareable. What I am trying to say here is we are trying to make mutual exclusion false. How we can make mutual exclusion false? We can make all the resources can be shareable. If it is possible, deadlock will be prevented. In brief, mutual exclusion is a condition that when a process is making use of one resource, that resource cannot be used by any other process. In case of non-shareable resource like printers, we cannot allow more than one process to access it at the same time. So, in case of non-shareable resource, mutual exclusion has to hold. Mutual exclusion is a condition that we cannot totally avoid. In general, we cannot prevent deadlock by denying the mutual exclusion condition because some resources are intrinsically non-shareable. We are discussing about deadlock prevention, and for deadlock prevention we see that mutual exclusion is one condition that must hold for a deadlock to occur. If we can avoid this mutual exclusion, then deadlock will never occur. But we see that we cannot avoid mutual exclusion altogether because there are some resources that cannot be shared by different processes at the same time. Hence, mutual exclusion has to be there. So, we can say that mutual exclusion is not the condition that cannot avoid it, and hence we cannot prevent deadlock by avoiding mutual exclusion condition. So, deadlock prevention is not easy to be done by avoiding mutual exclusion. Now let's go to the second condition. Second condition that we have is hold and wait. Hold and wait is a condition where a process is requesting for some resource, and when it is requesting, it is also holding some other resource. So the process is holding some resource and is waiting for some other resource. So that is what we mean by hold and wait. Only when a process is not holding any resource, it can request for a no resource. So we are trying to see now if we can avoid hold and wait so that deadlock never occur. In order to avoid hold and wait, we have to ensure that whenever a process is requesting a resource, it does not hold any other resource. One protocol that we can use for achieving this is before a process begins to its execution, it has to request all the resource that it is going to require during the course of its execution, and it must allocate all the resource before it begin to its execution. Only after it get all the resource, it will be begin its execution. For example, let's say that a process that require the disk drive and the printer. Instead of requesting them separately, it will request before execution. That is one protocol. Now let us see another protocol. An alternate protocol allows a process to request resources only when it has none. A process may request some resource and use them before it can request any additional resources. However, it must release all the resources that it is currently allocated. That means only when a process is not having any resource with it, it can request for another resource. So holding is not happening. It will first release everything, then only it requests for new. So we see that hold and wait can be avoided by following either of these protocol. But both of these protocol have two main disadvantages. That are first one is resource utilization may be low, and the second one is starvation is possible. Let us see here first protocol that we saw that a process is going to first get hold of all the resources that it needs, and then only it begin its execution. For example, a process need disk drive and the printer. First it will keep all the resources with it, then only it starts its execution. Let's say first of all it is using the disk drive. When it using the disk drive, the printer is remaining idle because it is right now using the disk drive. So we see that resource utilization is low here. And the second disadvantages is starvation. Consider the second protocol. When it requests for a new resource, it has to release all the resources it already hold. Let's say that the process need the resource back again. So it is going request them again. But it is being held by some other process. So there we see starvation. Now let us go to the third condition, that is no preemption. What is preemption? When a process is making use of some resource, no other process can take away that resource from the process. For preventing deadlock, we want to see if we can avoid preemption. If we are avoiding no preemption, what does it mean? It means preemption should be there. So the opposite of no preemption is preemption. To ensure that this condition does not hold, we can use the following protocol. If a process is holding some resource and request another resource that cannot be immediately allocated to it, that is, the process must wait, then all resources currently being held are preempted. Here we see that preemption is happening. If preemption is happening, what will happen? The process will not keep waiting for new resource by holding previous resource, but it release everything. Some other process can make use of those resource. So that is what we mean by this protocol. Alternatively, if a process requests some resources, we first check whether they are available. If they are, we allocate them. If they are not, we check whether they are allocated to some other process that is waiting for additional resource. If so, we preempt the desired resources from the waiting process and allocate them to the requesting process. Now let us go to the fourth and final condition. The fourth and final condition that we have is circular wait. What was circular wait? For example, we see that a process P1 is requesting for a resource R1 and resource R1 is being held by process P2, and P2 is waiting for another resource which is being held by another process, say P3. P3 is again waiting for resource R1 which in turn is being held by P2. So we see that there is a circle. They are waiting in a circular fashion. One process is waiting for a resource which is being held by another process. And so it is forming a circular pattern. So this is another condition that must be there for deadlocks to occur. If we can able to avoid circular wait, then also we can prevent deadlock. Let us see how we can prevent circular wait from happening. We need to impose a total ordering of resource types. That means all the resources that are there will be given some order. We will be numbering them using some numbers. Let us say that we have 5 resources, numbering them as resource R1, R2, R3, R4 and R5. And we will require that each process will request resource in increasing order of enumeration. That means if process P1 is requesting for resource R2, let's say, then it will be able to request next resource only in increasing order of enumeration. That means it requests for R2. So next resource that is request should be having a higher number than R2. That means it should be either R3 or R4. It cannot request for a resource that is having a lower number. That means it cannot request R1. So that is an example. Let us take another example. Suppose a process P1 is allocated to resource R5. Now if P1 requests for resource R4 and R3 which are lesser than R5, such request will not be granted. Only request for resource greater than R5 will be granted. Then the circular wait will not happen. So circular wait will not hold if we follow this kind of protocol. Here it says developing an ordering or hierarchy in itself does not prevent deadlock. It is up to application developers to write programs that follow the ordering. That means just giving numbers to the resource, it will not prevent. Only deadlock will be prevented if the application programmers develop their application in such a way that this rule that we mention here will be followed by their applications. So this is what should be followed in a circular way. So this is the way deadlock prevention can be done by avoiding one of this condition, and this is the way how each of the condition can be avoided. Thank you for watching.